Hello, everyone. My name is Wesley Brewer. Today, I'm presenting on the topic of production deployment of machine-learned rotorcraft surrogate models on HPC. I've collaborated with many people on this project whom I'd like to acknowledge now. Matthew Boyer and Ben Parsons from the Department of Defense HPC Modernization Program, as well as Daniel Martinez, Dylan Jude, and Andy Wissink from the U.S. Army DevCom Aviation and Missile Center, and also Junshi Yin and Valentine and Entourage from the Oak Ridge National Laboratory Leadership Computing Facility. So the U.S. Army DevCom team develops and maintains a computational fluid dynamics or CFD code called Helios that is used for the design and analysis of rotorcraft. Since high fidelity CFD can take weeks to run on supercomputers, one of the projects they have been working on is to develop mid-fidelity machine-learned surrogate models to speed up the analysis considerably. The way it works is that velocities are interpolated from the CFD grid onto a set of sensors around the blade, and the extracted sensor velocities are fed into a neural network, which you can see here at the bottom, in order to predict the pressure, CP, which gets mapped from a 2D layer back to a 3D blade geometry. From the blade pressures, force coefficients may be computed, and then Gaussian projection is then used to map these forces as source terms back into the Cartesian grid. So developing a model such as these is one area of research, but how to actually deploy these models onto HPC is a whole other matter of research, and that's the topic I'm going to be talking on today. So there is a growing trend of research in augmenting CFD codes with machine-learned surrogate models. So for example, the work by Pal et al. For developing radiation models, or Malek et al. For developing TensorFlow Foam, which is augmenting OpenFOAM to be able to call TensorFlow models. The work of Martinez et al. In developing rotorcraft models, and the work of Bouchon et al. In developing turbulence models. And there are also a number of solutions for deploying typical machine learning systems to the cloud. And when I say typical, I mean like object detection or image classification systems. So there are solutions such as the IBM's Power AI Vision Inference Server, Nvidia's Triton Inference Server, Google's TFX with TensorFlow Serving, Facebook's TorchServe, and Redis's RedisAI. However, there's a lack of literature related to optimally deploying such models on high-performance computers, with one notable exception. That is the paper by Partee et al. Called Using Machine Learning at Scale in HPC Simulations with SmartSim. This is a product that's being developed by HP Cray Labs. So how does typical machine learning deployment on the cloud differ from production deployment of machine learned surrogate models on HPC? So in the cloud, typically these systems are distributed or deployed via Docker containers, and they use Kubernetes orchestration for being able to do load balancing and scaling up and those kind of things dynamically. Typically, various types of data is used and from various sources, and typically the inference request comes stochastically. And in these types of scenarios, typically multi-tenancy and high throughput is important. On the other hand, for machine learned surrogate models, what I'm calling MLS models, production deployment, these are typically deployed on HPC, and they may be deployed directly in bare metal or using Singularity containers as opposed to Docker containers. Instead of using Kubernetes orchestration, typically job schedulers are used, such as PBS, LSF, or Slurm. And instead of various sized inference requests at stochastic intervals, generally you have fixed size inference requests at fixed arrival intervals. And instead of multi-tenancy and throughput being the most important metric, actually the time to end inferences, which I'll discuss later as a metric, is how fast can we inference in inferences is the most important metric. Our two main research questions here are how to optimize the time or minimize the time to inference in inferences, and how to achieve good parallel scaling performance. So understanding such issues as these will be key in designing efficient future systems. For this paper, we used two IBM Power 9 systems, one from the Department of Defense called Scout, which stands for Supercomputing Outpost. Scout is a supercomputer that's in a shipping container that's completely transportable to anywhere in the world to provide AI support at the tactical edge. It has 132 Nvidia V100 GPUs for training and 512 T4 GPUs for inference. And of course, it uses the Power 9 CPUs with 160 logical cores. And from the Department of Energy, we're using Summit. Summit is currently ranked #2 on the top 500 list. It has over 27,000 GPUs and 200 petaflops of peak computing performance. So one of the goals of this work is to understand how to optimally deploy machine learned surrogate models on these types of machines. So in order to do that, we need to understand what kind of factors affect inference performance. These include inference frequency, the inference payload, so which is the network input size times the batch size, the size of the neural network in terms of the number of trainable parameters, the communications protocols we use, such as HTTP, gRPC, or the Redis serialization protocol, RESP, whether we're doing the inferences on the same node or from making the request from another node, and the inference query type. So if we're doing real-time or online inferencing, or sometimes I call this embedded, so where you actually embed the function, the inference call in the code itself directly, like the TensorFlow call in your CFD code directly, as opposed to batch or offline inferencing, where you're actually sending a batch of requests to possibly another server to inference and batch, or streaming. Also, any kind of graph optimization, such as using TensorRT or TensorFlow XLA, should have a substantial impact on inference performance. And finally, the model precision. So whether we're using FP64, FP32, FP16, or N8. In this work, we've used a client-server architecture for deploying the trained surrogate models. Then we can measure the performance from the client side, which is what we see here, so that we have a CFD solver running on the client, and we have an inference server running on the surrogate model node, or a server node, another node, separate node. And these also can be actually on the same node. For a CFD code, at each time step, we would perform a number of inferences here, typically in the form of a package as NumPy arrays. And this gets received by an inference server, which actually performs the inference on the GPU and then returns back the results. And so we developed a benchmark system called smiBench, which stands for Surrogate Model Inference Benchmark, where we can study the inference performance while studying a range of factors. So essentially, we replace the CFD solver here with a code that generates synthetic data and measures the time it takes to actually send the request until the request comes back. The interesting thing about this benchmark is that it stresses the various components within the system, including the CPU, the network, and also the GPU as well. And we can use these results to find the optimal configuration for deployment. So in this work, we tested 3 different types of inference servers. So we tested Python Flask, so we developed our own custom inference server using HTTP protocol. We also used TensorFlow Serving with the gRPC protocol. And we also used RedisAI with the Redis serialization protocol, or RESP. In order to be able to scale out on such a system as Summit, we investigated various ways of distributing the workloads by using something as simple as a Python thread pool. We use this with our HTTP server. We also used HAProxy load balancer, which we tested with TensorFlow Serving. And finally, we used MPI for Pi, where we can do a scatter and gather. And this is what we used with RedisAI. As I mentioned before, we developed a simple benchmark system called smiBench, which stands for Surrogate Model Inference Benchmark. We have included a simplified version of the benchmark in the appendix of the paper. You can see a portion of the benchmark.py code here, and you can see one main loop here where we basically loop over the number of inference requests here, args.in, and we first generate some random data, and then we make an inference call here. And this is surrounded by timestamps just before and after, so we can compute the latency of the actual inference request. We actually have designed a SMI, Surrogate Model Inference class here, with methods for performing inferences using different approaches, such as HTTP, gRPC, or RESP. So no matter what approach we use, we first instantiate the SMI class, and then we define what kind of inference function we want to use. And so the way we define that each inference function is by using a Python closure, which is essentially a function within a function. So this allows us to only change one line at the top of our CFD code to affect which type of method we're going to use to do the inference approach. And so we don't have to make a lot of different changes in different places where we actually make the inference. So when I make the call inference here, it's actually using this function here. And for the HTTP case, when this inference call is made, The first thing we're going to do is we're going to serialize the payload using Pickle, and then we're going to use the Python request module to post a request to the inference server, which is going to receive the data and deserialize it, and then actually perform the inference and then return the results. We can do the same kind of thing instead of using our gRPC inference method here. And you can see here that the gRPC inference function is more complicated than HTTP here. And we can do the same thing again using the RedisAI with, in this case, we're using the client module from SmartRedis, and this is part of SmartSim that HP Cray Labs has been developing. The next thing we need are some rotorcraft surrogate models to test. We chose 3 different surrogate models at 3 different orders of magnitude in terms of number of trainable parameters. Note that these are real models that are being used in rotorcraft analysis. The smallest model here is an LSTM model. It has a number of LSTM layers. It actually has 9 layers and about 2 million parameters. The medium model uses 2D convolutional layers with 33 total layers and 44 million parameters. And the large model is a temporal convolutional neural network, or TCNN, and it has 96 layers. And basically it has a 1D convolutional neural network sandwiched between encoder and decoder regions. These are composed of Keras time distributed layers. We first look at benchmarks that we performed on Scout using HTTP over InfiniBand. And at first we looked at comparisons between performing inference without using an inference server at all, what I call the embedded inference approach, where you just import TensorFlow into your CFD code. So we computed the throughput in all of our paper actually using this type of formula. So the batch size is the number of samples per request times the number of inference requests we make divided by the total time it takes to make all these inference requests. And so for our smallest model, we found some interesting results here. So we have the throughput in samples per second on the y-axis and the batch size on the x-axis. And notice that the y-axis is log 10 scale and the x-axis is log 2 scale. So actually, while it looks like this is getting linear increase as a V100 with the batch size, this is actually exponentially increasing if you turned off the log scale. Another interesting finding for this is we actually found some cases where the CPU actually outperformed GPU, and that was for a small model at batch size of 1. But in most cases, the CPU underperforms the GPU. And I know with Power 10, there's a lot of focus on actually using Power 10 for inference, and there seems to be generally a desire to move inferencing to CPUs, which may work well only in certain scenarios like small models and small lightly loaded models. And I'll show later some issues with GPUs in terms of GPU underutilization. As far as the medium model, we found an interesting result in the medium model. While that we would expect that the embedded approach would always outperform the distributed approach or the inference serving approach, we actually found that the inference serving approach actually outperformed the embedded approach for a number of batch sizes in this specific model from 2 to 16. Here, there's a wider gap between our CPU and the GPU, and you can see a clear separation here between the embedded approaches on the GPU versus the inference serving approaches here at the higher batch sizes. So this most likely has to do with network latency, and you can see here the difference between using NVLink and on our T4 GPUs use PCIe 3. And finally, for our largest model, we saw another interesting results. We saw even more separation between the P9, even performs worse as compared with the GPUs. And another interesting result for the largest model was that we saw a clear separation here between the V100 and the T4 GPUs. And so for very large models with large payloads, actually the V100 significantly outperforms the T4 GPUs. And so our conclusions here were that the P9 significantly underperforms GPUs except in rare cases. Embedded inferencing outperforms distributed approaches except in rare cases. And the V100 significantly outperformed T4 GPUs for large batch sizes. Given that for a CFD code, our goal is to minimize the total amount of time to a request per CFD time step, we developed a new benchmark metric called T2NI, which stands for the time it takes to complete in inferences. We believe this is a more relevant performance metric for surrogate models because at every CFD time step, we typically need to compute n inferences, where n is typically the number of grid points in a domain. So this could be millions or even billions of grid points. And so the way we actually implemented this was through a bash script, where we actually take a timestamp and then we launch a number of inference requesting clients in the background. And then we have a barrier to wait till they all finish. And then we can take another timestamp and compute the difference here. We can demonstrate how the batching affects the T2 performance. So we start here with 128 inference requests of batch size 1. And then we keep doubling the batch size request and correspondingly halving the number of requests. So we end up with a single request with batch size of 128. Of course, in reality, we want to use a much larger batch sizes than this, but I show this just as a demonstration. So in this simple example, we observe speedups here. If you divide the number here by the numbers here, it shows speedups of 131, 73, and 20 for the small, medium, and large models respectively. So going from the 128 batch size 1 request to the single request of batch size 128. We also investigated increasing the concurrency as a means to reduce the T2 benchmark. So in this case, we're using n of 32,768, so 32,768 inference requests. And these top two actually we performed on Scout. The left one was on T4 GPU and the right one on V100 GPU. So here are the lower numbers better because we're trying to minimize the total time it takes to inference the 32,000 requests. And here we have using 1 GPU, 2 GPUs, and 4 GPUs. And again, here we're using a Python thread pool to actually implement the concurrency. And we did the same test on Summit. On Summit, we couldn't use HTTP because of policy reasons. And the interesting thing we found is that the increased concurrency here with gRPC actually destroyed our scalability. So you see you get good scalability here. And actually with increased concurrency, actually you see the T2 decreasing. But with gRPC, actually, in many cases, we didn't see much improvement at all. Actually, in many cases, we saw the best results, a concurrency of 1 using gRPC. And actually, we didn't see the scalability here. There is no scalability. It's terrible. From the previous studies, we actually found that the real strategy to get the good performance, especially with TensorFlow Serving and gRPC, is to use the maximum batch size we can and minimize the concurrency. So in this case, using a concurrency of 1. So I did a study of how large a batch size each of the models could handle. And so for our smallest model, we went up to a batch size of 262,000. For the medium model, the batch size was 2,048. And for the largest model, the batch size was 1,024. And we ran these on Summit up to 192 GPUs. And actually, we observed good parallel scaling efficiency. It starts to fall off at 96 and 192 GPU, the higher GPU counts. But actually, we achieved 1 million inferences per second here at our smallest model at 192 GPUs. We also wanted to investigate what kind of speedups we could achieve by optimizing our results using TensorRT. So TensorRT performs a number of optimizations, including freezing the weights, fusing the layers in the network, quantizing the weights to lower precision, and calibrating the weights for N8 inferencing. We had difficulties converting all of our models, so we tried with 2 different approaches to convert the models, writing our own code with TensorFlow TensorRT and also using the save model CLI utility that comes with TensorFlow. So we were only able to test using TensorRT successfully on our smallest model, which gave pretty significant results, 3.3x speed up. You can see here for V100, 2x speed up on T4 GPUs, and 2.6x speed up on Power 9 GPUs. We performed another study on Scout where we just compared RedisAI using the Redis serialization protocol directly with TF serving using gRPC. In this case, we send 512 requests with batch size 1024 per GPU and average the latencies to get throughput. Here again, we see single-threaded concurrency, which is the solid line here, almost always outperforms multi-threaded concurrency, so concurrencies of 1 and 2. And we see that RedisAI significantly outperforms TensorFlow Serving. And so the left plot is for the V100, and the right plot is for T4 GPUs. And so we have the throughput in samples per second on the y-axis and batch size on the x-axis. So in this case, the conclusion was single-threaded concurrency almost always wins, which is what we concluded from other experiments we ran, and that RedisAI outperforms TF serving. And this was really only true when we used the Python API. So we actually ran these tests again using C++ clients as well. And we basically came up with a ranking of all the different approaches between RedisAI and TensorFlow Serving. And so we see that embedded C++ is the fastest approach, which is expected, but the next was TF serving with the C++ client, and then embedded Python, and then the RedisAI with the C++ client, RedisAI with Python client, and then TF serving with the Python client came in last. One issue I wanted to mention that we experienced in all these studies is that we found with small neural network models, there's a problem of GPU underutilization, especially for very small models. Essentially, the system becomes GPU IO bound. Inferences are occurring faster than the data can actually get to the GPU. So we actually did some testing trying to implement concurrent inference servers per GPU. So multiple TensorFlow serving instances bound to a single GPU. This kind of test actually showed that the concurrent servers improved the GPU utilization, but the inference performance actually worsened. So more study needs to be done in this. And just as a last point, I wanted to mention that besides performance, there's a number of other good reasons to adopt an inference serving approach. Basically, it makes good sense from a software engineering viewpoint. And so the inference serving approach, as compared to embedded approach, actually implements several important principles such as separation of concerns and also just having a microservice architecture, which a lot of production level systems have moved to, especially since the rise of containers. So for conclusions, we've demonstrated how to perform optimal deployment of surrogate models on HPC. So we found for HTTP over InfiniBand, concurrencies of 2 or more with maximum batch size where it was optimal, while as for gRPC and RESP, concurrency of 1 with maximum batch size was optimal. We showed good weak scaling efficiency up to 192 GPUs per node using the HAProxy for load balancing. And we did a study comparing directly RedisAI with TensorFlow Serving. We saw that RedisAI outperforms TensorFlow Serving when using Python clients, but TensorFlow Serving outperforms RedisAI when using C++ clients. We also mentioned the issue of the tiny or small neural networks suffer from GPU underutilization. And finally, inference servers implement software engineering best practices such as service-oriented architecture and separation of concerns. I will take any questions now. Thank you.